Okay, this is a quick seminar solution for 625. We're looking at the differential amplifier. This diagram I've got here basically shows the differential amplifier that we're going to design. Let's over-annotate a few things. The specification says we have 15-volt supply and negative 15-volt supply. And we have our ground at the input. The specification, so we've ticked off those two. The input DC is at 0 volts, so I'm going to consider that these two bases are at 0 volts. I know that there's a small amount of current, we could call that IB, flowing into the base to support the collector current, but at the moment we're going to assume that these resistors here, I'll call them RB, are just there to balance the input from this voltage source here, Vin. Okay, I'll label this transistor Q1 and this one Q2. Let's put more on the specification. The specification also says we have a tail current of 3.6 milliamps. Let me explain why we're calling it tail current. The differential pair is often called a long tail pair, or a Royal differential, so this is where we create our tail current source. Kirchoff's current law, the KCL, says that current in is equal to current out. Therefore, I've got a collector and I've got another collector which effectively are feeding current into this circuit. I can therefore say that collector current Q1 is equal to collector current Q2, which is equal to the tail current over 2. Okay? Putting the maths very simply, I've got 3.6 milliamps divided by 2, 1.8 milliamps. Okay? That is the current that's flowing in the collector. So I now know what's going on here and here. Okay, on these two devices. My output DC says I've got 1 volt. Okay, 1 volt DC at the output. So I've got 1 volt here and 1 volt here. So now I've got everything I need on this circuit diagram to do the design. Let's start off by doing the design. Let's have a look here at what the value is at the emitter. VE must equal GND, or 0 volts, minus VBE. Okay, because we've got a volt drop in reverse. Now normally we would say that VBE is 0.7 and it's a good approximation. Today we're not going to do that. We're going to say that VBE equals VT natural log IC upon IS. When we do that, we've now got to actually put all the numbers in the equation. VT is known as thermal voltage, KT upon Q. Our general guideline or rule of thumb is that's 25 millivolts at room temperature. Our collector current is known as 1.8 milliamps, so I can write VBE equals 25 millivolts natural log 1.8 milliamps divided by the saturation parameter of this transistor. They were given 14.34 E minus 15. Okay, so I've now got my number here. So if I punch that into a quick calculator, I'll be able to find out exactly what that number is. I make that 0.64 volts. Okay? So I now know the voltage at this node. 0.64 negative. Okay? At that node. I know the volt drop here on the RT, and I know the volt drop here on the RT. The RT. So I can now define RT, the resistance in the tail current source, is equal to negative 0.64 minus 15. So I've got the negative sign there, divided by the total current, 3.6 E minus 3. If I put all those together, I now get 3989 ohms. Okay, I'm going to call it 4 kilo ohms. Okay, is my design. So I've now designed this component, RT. I now need to design the collector component. Now in the specification, we didn't have anything in the specification at all about the actual value of gain. So we're going to find out what the gain is from this design. The key thing we've got here is V out DC is 1 volt. So the collector resistance is equal to the supply, VCC, minus the voltage at the collector, which is part of the spec, V out DC, over the collector current. So that is 15 minus 1 over 1.8 E minus 3. So that's 14 divided by 1.8 E3 minus, and we work that as 7777 ohms. Okay, I'm going to abbreviate that one to 7.8 kilo ohms. My key number. Okay, we have now designed this differential amplifier. Okay, with those two values in our circuit. What we now need to do is we need to find out what the gain is going to be for this design. We're really interested in the combination of both ADM, differential mode gain, and ACM, common mode gain. Well, here's I've just done a quick aside. Okay, the small signal equivalent model of this transistor, here's the collector, the base, and the emitter. Here is the base, the collector, and the emitter. We have a value RBE, the input impedance, and we have a value IB beta, which is my current source. Now when we put that together with this differential, we have to remember a few things. The collector, I'll just put a highlighter on here, my collector goes all the way up and down to ground. Okay, so my collector is connected through RC, through this voltage source here, which effectively behaves like a short circuit. So my collector is connected to ground through RC. This connector is connected to ground through RC. My emitters are connected to each other, so they're simple, and my input signal comes in on the base. My emitter goes through RT to ground. Okay, so because we're going back down to ground again, we've got a simple sort of circuit here. This is my design here. So this is what I've drawn. This transistor here, this part, is Q1, and this part here is Q2. I need to accommodate this resistor. Let's have a look. I need to accommodate RT. What do I do? Should I put a resistor in here or not? Is it there? Right, now we need to do a little bit of a thought experiment. Okay, I'm going to draw some little symbols on here. If I put a sine wave on one side of the differential amplifier, for a differential gain, my other input will be a minus sine wave. So here's sine, here's minus sine. If the sine waves propagate down to the emitter, what happens with a sine and a minus sine? You get 0. If you get 0, this is behaving like ground. Therefore, for differential, or for differential gain, RT equals 0, a short circuit. Okay, that's very important. If that's the case, we can now simplify the design. Okay, what I'm going to do, I'm going to draw that simplification. I only need half the circuit to get my output. So I can say that AV of half the circuit will be equal to ADM, which will be equal to V out over V in. Let's write an equation for V out. V out should be, if I look on this circuit diagram, V out will be proportional to IB beta RC on one side. Okay, let's write that down. Okay, the negative sign there basically just shows you've got phase inversion. So when I've got my signal here, it will be it'll have an amplification factor and it will be inverted at the output of that first stage. If I write out V in, V in effectively is simply the current times RBE. IB, RBE. Okay, now we can expand that a little bit, because if we remember our second year work, that's IB 1 plus beta RE. Okay, so we're magnifying the emitter resistance to get the base emitter resistance. Okay, and that's our simple design. We should remember that RE is equal to VT, thermal voltage, over the emitter current. So, if we put all of that together, we now have that AV equals ADM is equal to minus IB beta RC over IB 1 plus beta RE. And of course, what we can do now, we can cancel IB, and we can cancel IB and beta and 1 plus beta, because they are effectively the same number. we are left with ADM for this design, the differential mode gain, is minus RC over RE. We'd probably drop the minus sign and just go modulus only. Let's plug in some numbers. Let's find out what ADM actually equals. Magnitude only, we don't care about the sign. So our RC value was here, 7.8K. Let's plug that in. 7,800 divided by, in this case, RE. RE is VT over IE. So that's 25E minus 3 divided by 1.8 E minus 3. Okay. Remember, we've got the emitter current being almost the same as the collector current. Let's just define what RE is first. So that's 25 millivolts divided by 1.8 milliamps. It's 13.8 recurring ohms. Let's say 14 ohms. So ADM is 7,800 divided by 14, 557. Okay, so this is a very large gain. If we go back to the specification, okay, we actually had a signal of 5 millivolts going in here. I'll just write that on there, 5 millivolts. So now what's our differential signal coming out then? V out differential is equal to 5 millivolts multiplied by 557, which is equal to 2.78. Okay, so this is a large gain, which is ADM, differential mode gain. Well, what we need to do now is we need to do this circuit again here that I'm highlighting. We're going to redraw this circuit, but we're going to consider it for the common mode gain. Common mode gain is different. So let's draw out the topology again. Here we have transistor 1. Here we have transistor 2. RC, RC, V out 1, V out 2, V in 2, V in 1. VCC. Okay, but where does the emitter connect? That's RBE, RBE, IB beta, IB beta, IB, IB. Okay, for common mode, remember in the differential amplifier, we actually had a sine wave and a minus sine wave coming in, as indicated here. In this case, we now have a sine wave coming in, and we have a sine wave coming in, because we've got the same signal. If those signals propagate through to the emitters, what will happen? They will wave reinforce, and the gain signals will reinforce. So this time, we can't ignore the value of RT. We have to include it in our design. We don't cancel those two signals. Now, when we do that, we want to try and simplify this design yet again. This is my ground, this is my ground again. So what do? Well, let's just go on the side here. If I have two resistors in parallel of 2 kilo ohms, that is equivalent to one resistor of 1 kilo ohm. So if I want to split this resistor RT into two parts and then concentrate on half the circuit, what effectively I've got to do, I've got to double that component. So I'll just draw it in separately. If I remove RT, I have 2RT, 2RT. I've now got half the circuit, and this is a simplified model from where we are. So when I just draw that back out again, what we have is our transistor, IB beta, RBE, IB, and now we have my output. Here we have RC, and here we have 2RT. What I'm doing here is my input and output. Now you'll probably recognize that as the feedback controlled gain circuit. So let's write out my gain. AV will be ACM, the common mode gain, which is V out over V in. Let's write V out. V out will be this Kirchoff's law loop round here, which will again be minus IB beta RC. Let's write V in. V in's a little bit more complicated this time because V in has got a volt drop across RBE and it's got a volt drop across 2RT. Let's write out each one. The first one is IB RBE plus, now we've got to consider Kirchoff's current law. We've got current coming down here, IB into the node, and we've got IB beta into the node. So we need to think about both of those. So if we add those together, we've got IB 1 plus beta 2RT. Okay? And there's our term. So if we just divide those through, we have effectively found ACM, or AV for this circuit, is equal to minus IB beta RC over IB. I'm going to expand RBE, 1 plus beta RE, plus IB, 1 plus beta 2RT. And of course, now what we can do is we can cancel, because IB is everywhere, beta and 1 plus beta is everywhere, and because of that, we've now got a much simpler equation. So the common mode gain of this circuit is minus RC over RE plus 2RT. We can say that RE was 14 ohms is significantly smaller than 2RT. RT was 4 kilo ohms. So we can almost ignore that term. Let's just do a quick calculation and plug some numbers in then. ACM. If we go for magnitude only, we can drop the minus sign. 7,800 divided by 14 plus 2 times 4,000. Okay, if we punch that into the calculator, we have a gain of 0.97. Okay, so we have a gain that is less than 1, which is attenuation. Okay, and that's what you want. Okay, we want this. We want to reduce the common mode signal and amplify the differential mode signal. So the last piece of work is common mode rejection ratio. It's defined as the differential mode gain over the common mode gain. We had 557 divided by 0.97. Okay, which equals 574. Okay, there is my CMRR, common mode rejection ratio. Normally we express common mode rejection ratio in decibels, 20 log to the base 10, 574, which equals 55.2 dBs. Okay, let's just recap. 2 transistors, 3 resistors gives you a CMRR of 55 dBs. If you were looking at a 741 op-amp, okay, you would have, I don't know, 50 transistors, a dozen or so resistors, much more complex, and its CMRR is 90 dBs. So with a tiny amount of design work, we have got, almost halfway to the performance of a 741 op-amp with this relatively simple circuit. Okay, let's just go back to the top here. This very simple differential amplifier now gives us quite a respectable sort of design. I'm going to do something else now. I'm just going to draw out a couple of comments. ADM, differential mode gain, magnitude only, is the collector resistance over RE. If I want ADM to go up, I would have to make RC go up or RE go down. For RE to go down, I would have to make IE go up, because I can't control thermal voltage. So those are my options. If I want ACM, magnitude only, is RC over RE plus 2RT. If I want ACM to go down, as we've just said, what do I do? Realistically, I have to make RC go down, which is in contrast to the ADM, or RE has almost no effect, RT must go up. If I wanted to affect the current, I have to make the current go up to affect the reduction of RE, which would then mean I'd have to make this resistor smaller. So to improve the design for CMRR, we're stuck. Okay? Any choice that you make to increase the resistance, RC, will affect the opposite one. Any choice to move the emitter current up, or the tail current up, will affect the other one. What do? Solution. A voltage source, 0 resistance, or it's in the milliohms region. A current source, infinity resistance. Therefore, if we replace RT with a current source, we will increase RT, but not affect IT. Therefore, CMRR goes up. In fact, with a really simple current source, just basically a transistor, something like that, with a locked voltage here, we can pull a specific current quite quickly, quite easily, and then we can improve that further if we want. That would add 20 dBs to your design. So there we go, that's the first part of that seminar. The key thing to remember here is common mode rejection is differential. I'll just highlight this, and I'll highlight in a different colour. Common mode rejection is differential over common. Okay. We tend not to express it in unity terms, we tend to put it into decibels, and our simple designers achieve 55 dBs. If we want to increase ADM, our choices are collector up or basically current up. If we want to affect ACM, okay, and of course we want ACM to go down, we either have to make RC smaller or we have to make RT bigger. We can't do that with the design that we've got. Our solution is to use a current source. And the simplest of current sources is a single transistor. Okay, we will cover more of that in the next screencast, where we're looking at changing just one component. We're going to remove this component here, RT, and we're going to replace it with a current source. And when we do that, that current source will have a much higher impedance, still pull the current, and our circuit will work as we expect.